So, are we okay? All right. So before we go into the details, I figured I want to tell you a little bit more about myself, especially what I did before I got here. So I moved. I am an international student. I moved to from Vietnam to Minnesota in 2017, and pretty much started working with the space physics group. But I had a pretty wide range of interests, if you will. I spent a little bit studying about the history of science. I think that science is really cool because of the community and the people in it and how the thought process goes. So I wanted to learn more about that. And then I spent a little bit of time in the philosophy and math department as well. The philosophy of language actually is pretty interesting because it led to the formal development of predicate logic and set theory. So that immediately ties into the modern development of mathematics. So then I jumped ship to math and studied a little bit more about the details. I got really good at math, but this period was kind of like an exploratory period for me. I was kind of lost for a while because I was doing so many things at the same time. I stretched myself too thin. So I figured I need to go back to my original motivation, which was physics. And that's when this project starts, actually. Yeah, it's a cornerstone for me because I remember talking to a high energy physics professor, and he said something that I'll never forget. He told me, there's always going to be struggles in everything you do, but you get to choose the types of struggle you want to live with. And this turns out to be what I wanted to live with. I like two things, which is to learn physical theories and to do computations to verify those theories. So that's what I did when I was teaching for a while as well. That was really random. But yeah, so 2019 to 2020, that was a period where I thought about myself, and after that, I started focusing more onto what I wanted to do. And I started saying no to some of the opportunities to actually do stuff I wanted. And that was the phase where I focused more on theoretical development. And that's when everything about this project started to play. It's been a while of struggling, but, and also I started fostering a cat. I'm not saying there's a correlation, but there is a correlation to doing theory. But yeah, so I started learning, doing serious theory, and also trained in high performance computing for a while. I got better at learning about supercomputing and learning to work with the multiple clusters. So that led to some pretty interesting side projects. And eventually all of those led me here. And hopefully I am going to get a lot out of it as well as undergraduate. So we'll see. All right, so the main question that we're going to deal with today is, how do we measure chaos? And the answer to it, the quick answer is, it depends on who you're talking to. And this is because chaos is a really multidisciplinary field, and you have an overarching field of mathematics dedicated to talking about only the abstract properties of it, and these sort of graphs actually demonstrate those kind of properties. But that's not what we're going to talk about today, because that sort of talk is going to be very technical and complicated, and I don't want to do that. So today we are going to be physicists, and we will do what physicists do best, which is to derive motivations from physical curiosity. We'll deal with a specific problem, with a specific system, and we'll see how chaos will emerge from it, and then we will try to describe it and quantify the behaviors that we're seeing. So I put this graph up here. You don't need to know about it for now, but it's kind of like my starting point as an undergraduate. Right? So my professor gave me the code, And I ran it, and I was like, "What the hell is going on?" Because it's in some of the cases it's has a periodic fluctuation, right? So after a period of time, you can see that. So this is a plot of kinetic energy in time, and after a period of time, you can see that the kinetic energy stays about constant if you average over it. But in some cases, it's doing stuff like this, which is in rigorous language can be called quasi-periodic, because it's doing something and then it stops and then it does it again, right? And then it's also stopped. But also it's unpredictable because if you look at only these two periods, you might say, oh, it's going to do it again after some time, but then after some time it does something completely different. So it's intermittent, it's unpredictable. What can we say about this as physicists? So we'll come back to this graph later and try to build some sort of intuition behind these sort of behaviors, what it's actually doing. Okay, and also, right, worse than so this was sort of like the expected behavior, and it's even worse because you can see that here in the chaotic case, it looks nothing like it, and it's kind of doing the same thing for a little bit. It stays kind of constant here, is fluctuating around some value, but in the expected case that my professor told me, we're expecting large jumps like this, which are pretty much well defined, right? Because it stays constant for a while, jumps up to a certain value, stay constant for a while. That's pretty well described. So that is the problem. Before we talk about certain problems, I like to talk about the scaling of the system as well. And if you're a physics major, you might have heard about interdimensional analysis, which is what we're gonna talk about in this slide. So this is kind of a slide for the sizes of certain things. So this is the size of a human here, and over here we have an atom, proteins, and whatnot. So it depends on the type of problem that you want to solve. Determining the size of your objects is very important, because from there you can identify the principles, the theories that you might want to work with. For example, if you're a chemist or a biologist, you might want it to be in this scale. If you're an engineer, a mechanical engineer, for example, you might want to deal with scales that can directly interact with a human, right? Like a car, a bridge, or a building. So in terms of that, let me take a little bit a step back and talk to you about the object that we're dealing with today, which is plasma physics, because we're dealing with solid wind, which is a plasma. So what's a plasma? It's a really hot gas, basically. You have a gas, you heat it up, the ions and the electrons start to do some things, and in collectivity, so we call it's like a swarm of bees. So it has some sort of collective behavior to it, but it's not completely random like every molecules in a gas. So here are some examples of a gas. You can generate a plasma. Sorry, you can generate a plasma with lightning strikes. This is the Crab Nebula, which is created by a supernova, and here you can see the shell of it and as the plasma, and those lines that you see are actually plasma shells pushed out from the supernova. And over here, the third example, we have the heliosphere. We have the sun, which is also a blob of plasma, and the environment around it, which we call the solid wind, is also a plasma. And around the Earth, we also have plasma everywhere. So I think it's somewhere around 90% of the observable material that is a plasma, in the state of the plasma. All right, and so because we're dealing with that, we need to identify the scales of a plasma. Right? Before, yes, as you can see, this is small, this is a little bit bigger, and this is really huge. So what is the scale that we're dealing with here? So here's a little bit of basics in plasma physics. In a plasma, we have ions and electrons. Those are positive and negative charged particles. And usually a plasma exists in a magnetic field. So if you've taken physics 2, this is one of the first things that you learn in magnetism, in that the particles would rotate around the field, like in that manner. So then from there, this is the scales that we're going to deal with, and it's called the dispersion relation. If you've never seen it, that's okay. The basic idea is, these different lines that I plotted, those are the multiple wave modes that can exist in a plasma. So think about a simple example like a spring, right? If I put energy or get energy from a spring, by stretching or expanding it, then it will act, it will respond in a oscillatory motion. Right? So same thing here. A plasma consists of these objects, and if I put energy into a plasma, these wave modes are where those energy is going to go, and that's the natural response of a plasma. So yes, I haven't explained the axes. So on the horizontal axis, we have frequency. That is defined by some characteristic frequency. So over here, for example, in the small scale, you have waves that are light-like, which is excited by the jiggling of a dipole. So if you learn about upper level E&M, you learn about that. And this is called the plasma electron frequency. That's a fundamental or the harmonics, the natural frequency of a plasma. So this is the point where the description of the plasma starts, in a sense. So beyond this, these waves are associated to plasma more than light. And then because we have 2 objects, we also have 2 natural scales, which is the electron frequency scale, cyclotron frequency, which is the frequency of the rotation of the electron. And then we have the ion cyclotron frequency here, which is also associated with to the rotation of an ion. So those are some of the scales, and that determines the description of a plasma. We can describe it like a gas in the kinetic range, or a fluid if we average over it and just look at the motion of the ions, because they're slow, because ions are much heavier than an electron. So that is the scale from large to small that we're dealing with. And so let's do a quick exercise. In this discussion, we're going to care more about the electron. So that's my subject I want to talk about. And so if we're interested in the kinetic electron dynamics, can you look at this graph with different wave modes and tell what modes should we look at? What is the wave that is going to interact with electrons kinetically the most? So talk to your neighbors a little bit and come back and talk about it more. Okay, anyone has an answer? Right, yeah, it is the Whistler wave, because it approaches the electron scale at the kinetic range. So that's correct. Also, it can also interact with ions, but we're not worrying about it here because we've defined our problem, right? This is the object we're interested in. And so naturally, this is the mode that is going to interact with it. And so a little bit more question?
Okay, just a question. So why doesn't it ever actually reach the electrons of the
Yeah, that's a good question. reaches the electron frequency at large wave number, which is small scales. That's a really good question. I don't know the answer to that, the immediate answer to that. Probably has to do something to do with resonance. This is my guess, right? Because at the resonant frequency, theoretically, you can have an infinite amount of energy transport between the wave and the particle, and that is really hard to achieve. So yeah, you would have to go to really large scales in terms of wave number to get that. But yeah, very thanks for the question. So a little bit more about Whistler wave. These are right-hand polarized electromagnetic waves. And what it means is right hand. If you take your thumb and put it into the direction of the propagation, then the fields, the electromagnetic fields, rotate in the direction of the curling of your fingers. So if you look at this rotating arrow right here, that's what it's doing. It's rotating like this, and the wave is moving forward out of the page. So a little fun fact about whistlers. It's called whistlers because when you can actually hear it. So when people were discovering about this wave mode, they were hearing whistler sounds from antennas on Earth. And these are generated by lightning strikes. So can you try to play the video? So this is what they sound like. Sounds like a whistler because the dispersion relation, it goes from high frequency to low frequency. So it makes a okay. All right. So those are the main objects in the plasma that we're going to talk about. There are two things: particles over here, and waves. Both of them can carry energy, and so the relationship between them is that they are transporting energy in a plasma around. They move it around. So a particle can be decelerated to generate wave modes. It grows a wave, and a wave can also give off energy to the particle so that it is energized when it's going at higher speed. So that is like the general mechanism for a plasma to conserve its energy internally through these two objects. An example of energy transport is something called turbulence. For example. That's what I'm doing right now. And turbulence, I think there's a little poem here that I really like because it describes exactly what turbulence is. It goes from large scale to increasingly small scales through these sort of eddies or these circular currents, we call them. So the poem goes: big worlds have little worlds that feed on the velocity, and little worlds have lesser worlds, and so on to viscosity. So energy is transported from this large scale where there's no wave, and then it trickles down to the smallest scale until there's no energy to transport to anymore. So an interesting thing is recently I started looking into satellite data more, and this blew my mind. So this is actual spacecraft measurements that I made. The first two panels are frequency versus magnetic and electric field energy density. So it's the energy that's being transported into the plasma. And the last panel is the same plot as before. It's a dispersion relation. So frequency versus wave number. And so you can see here, at the large scale, so energy is transported down to smaller scale until it reaches the kinetic scale, right? The ion cyclotron frequency. And then down here, you start to see a bunch of wave modes being generated. And those are Fane waves, ion cyclotron waves, and Whistler waves. So that's really cool. It tells you that energy is being transported down through turbulence, and then that when it hits the scale of an ion on an electron, it starts to generate a bunch of waves. So that's a plasma responding to energy being transported into it. Yeah, another example is the solar wind. The sun, as I said before, is a rotating blob of plasma. And as you can see here on the surface, there's a lot of activities that are going on. And that causes a really dynamic environment around the sun on the solar wind. So it can cause something like corona mass ejections, where you have a really huge blob of plasma being ejected out, and that could greatly alter the background field, magnetic field, like that. And within that sort of environment, it's also very turbulent, and it can cause wave modes that can, in turn, energize particles. So you can see energetic particles being shot out. Or a recent discovery from the Parker Solar Probe, which is the first man-made probe that goes to the closest to the sun as we've ever got, goes to something like 0.2 AU, which is really, really close. And it finds out that the magnetic field is doing something like this. It's whiplashing the sun is whiplashing the magnetic field, and it causes these kinds of switchbacks, which within those regions is also very turbulent, and you have a lot of cool dynamics going on. Now that we've talked about the solar wind, the larger context, let's talk more in details about the energy transport that can happen between the two objects. So here I have a slide to have us think about surfing. So Tyler, can you keep track? Keep track. Whoa. Okay. Cool. Okay. So I think we're going to be focusing on some person over here. So as you can see, if you're a surfer, a wave coming up to you and you're doing nothing, that's what we're focusing on. So that's the one person that's surfing the wave, right? So let's go back and try to see what is different for this surfer compared to the other ones that are just staying still and bobbing up and down as the wave move across them. So I think this one. All right, can you tell what they did? Anyone? You?
They paddled to match the velocity of the wave.
Right. Yeah, you have to paddle to have some sort of initial velocity, and then from there you can surf. So let's do a little bit more discussion about this. So to talk with your partner, if you have a wave coming through you like this, where do you want to be if you want to surf a wave? And the second question is, at which position? Think a little bit more about in terms of energy. At which position does your energy decrease or increase? Okay, let's start with your part. Come back. Okay, so let's come back and try to answer these questions. So anyone has an answer for these questions?
You want to surf on me like slightly in front of the wave.
Right. Yeah. So yeah, that's exactly it. If you want to surf and if you want to gain energy from the wave, you want to be here where you will gain if you surfer. So this analogy, a surfer is kind of like a particle. So the particle would gain energy here, but at the same time, if you're here, you're going to decelerate. And the opposite things happen with the wave, right? The wave loses energy over there, so it dams away. And here, it's gaining energy from the particle to grow. So this is a concept called Landau resonance. It happens when your velocity is the same as the wave's phase velocity at these two positions. Those are where you can exchange energy most efficiently where the wave is if it's moving longitudinally across you. Right? So, but our wave is not longitudinal. We have, again, an electromagnetic wave, which is doing something like this. It's rotating, right? So building on that concept, cyclotron resonance is a more general way to think about it. And the basic picture is, so an electron here, you can think of it as a left-hand particle, which means you put your thumb in the direction of the magnetic field, and it rotates in that way, right? And if you have a left-hand particle and a right-hand wave, you see they have to counter-propagate in order for them to exchange energy because they are doing the same thing. They're rotating in the same manner. So this kind of this GIF plots the position of the particle in red, and so you see if those two objects are doing this, the radius keeps increasing, and if you've taken E&M, you will understand a little bit more in terms of the force. So force is QE, right? So if the electric field in this case it's radial, so when the particle sees the same field as it's rotating, then it's gonna keep getting accelerated radially. That's why the radius keeps increasing like that. So also you can see here mathematically that's how it's formulated. This is the frequency of the wave. That's the electron cyclotron frequency. That's the parallel wave number times the particle's velocity. And n here is called the harmonics. It's just an integer that tells you the harmonics of the resonance that you're dealing with. So for example, if you set this to 0, then you get Landau resonance back in the other case, right? Because omega over k is a wave phase velocity, and this is just the particle's velocity. So they go back. That's the same equation that you have in the longitudinal case, versus a more general picture where you have a rotating wave. So, come again?
Can you tell us what all these different colors are?
Oh yeah, I think it's a little bit hard to see, but this is the electric field, and that should be the magnetic field. Wait, no, that is something. I can't see it. Sorry. Yeah, the label doesn't matter here. The point is, particle is doing that, and the wave is doing that. So the particle is seeing the same field at all time. So I think that's what it's supposed to say. All right, so that's the context. We've defined the general big picture. We've defined the objects, and we've talked about how those objects interact. It's time for demonstration. So I've made a simulation here, and this is not too clear. Can I? Oh, I can't do it. You're gonna have to click on it. Yep, and then pause. Drag it back to the initial. Okay, so this is a simulation I ran. In this panel here, we have the physical simulation box. So we're plotting the z position and x position. So all of the particles are going to start here, and these colors, the red and the blues, are the wavefronts in the simulation. So it's a sinusoidal wavefront. And over here, I'm showing all of the particles that I'm putting into the simulation. So they're categorized by their initial velocity. So red are the counter-propagating particles, and blue are the parallel propagating particles because the wave propagates in the positive z direction. Okay, and over here, I'm plotting the change in energy and the change in angle. And the angle is just the, the polar angle in this plot. So it is the angle that the velocity vector makes with the background field. All right, and when I run the simulation, I want you to remember this picture again. You have to counter propagate in order to exchange energy effectively. So Tyler, can you run the simulation? Yep. So as the simulation is run, particle is doing something. And over here, you see only the anti-propagating particles with the wave are energized and also scattered from its initial position. And all of the other ones don't care. So that's what's happening. Over here, you can also see, if you run the simulation again, you see that these particles are just trapped within the wave fronts. So those are like surfers, staying still and then just bob up and down as the wave moves past it. But these red particles, they're interacting resonantly. Again, with this picture, so it's so they are just riding the wave fronts and keeps getting energized by that much amount. Okay, so the next simulation that I have has the same sort of setup, but the wave amplitude is a little bit higher. So this is an important case because this is where you're going to see chaos emerging, because when you have a really huge wave, then all of this intuition just goes to the trash can, right? Because what the particle is doing is just being dragged along with a very huge wave. So you can't do anything. Although you're still, can you play it, Tyler? Okay. Although the particles are still being energized, but in the physical domain here, as you see, they're just being dragged along with the wave fronts. There's still some resonance interaction happening, but overall, generally, the particle is being forced to move together with the wave. Okay, so that is the simple cases. What I'm going to do next is, instead of this picture, I'm going to tilt the wave a little bit. So it's moving obliquely. That's what it means. It moves at an angle with respect to the particles. And as you see, if you have this picture, then the symmetry is kind of broken, right? Because now the field is doing this, while the wave, while the particle is doing that. So they can still interact resonantly in a sense, but it's going to be modified. So if we play the video, so you see the wavefront is a little bit slanted here, which means they're propagating obliquely. And in the energization and scattering, you see some particles are being energized, but it's not the ones that are counter-propagating anymore. So it's modified in some sort. Can you think of a way to determine these particles, what they are, in terms of the resonance condition? That's a hint. Anyone? So it's just the different values of this n. Right? So you can solve this equation for the parallel, and the different n's would determine the different resonant velocities that the particle might have where they can interact resonantly, instead of just this simple picture. So yeah, these particles, as we will see, those are going to be determined by the resonant parallel velocity in the next few slides. All right, so the last thing I'm going to do is cause chaos from this picture. So how can we do it? You can increase the amplitude. So that means right now you have these particles interacting with only a few wave resonance at a time, right? So these peaks are well defined, but if you overdrive the resonance, then can we go to the next slide? If we overdrive the resonance with a higher amplitude, then we are going to get chaos. All right, so originally they have some sort of coherence, but after a while you can see that these wavefronts are just bashing through the particles and causing them to move everywhere in phase space, is what we call it. So after a while you see, right, these particles are scattered everywhere, and also the energy that the particles might get is just through the roof. And it's also chaotic, right, because it's not a well-defined line. Right, so some particles still don't care, but most of them have a lot of energy being transported into their motion, and they are scattered everywhere. So there's large change in pitch in angle as well. All right, so that's the emergence of chaos. And to go back to the original figure that I showed you, these are the kinetic energy of a few particles in that simulation. So we saw a lot of particles in those, and then I went in and picked some out and then plot their kinetic energy in terms of time, and that's what they're doing. Some particles don't care about the resonance whatsoever, even though there might be a large wave, and some particles interact really resonantly with it. All right, so that is the problem, and now we have a few issues here to be mentioned. Right, first of all, the energy is usually not conserved, because if you're looking at just a particle, it's getting energy from the wave, right? So its energy is increasing in some manner. So in that case, how do we know there's nothing wrong with the simulation, right? Because I could just be messing up a line of code somewhere. I was a sophomore, so it was a really likely possibility. And also we need to quantify this sort of behavior in some ways. And I think at this point, there are a few questions that are popping up, and it depends on your which questions that you're more interested in, that says a lot about your intellectual curiosity. So at that time, I had three main questions, right? First of all, is anything wrong? Did I make a mistake? The second one being, we see these sort of intermittency and unpredictability. How do we describe it? And the third one is, what sort of physics is interesting from this picture? We can't say anything directly. So what, right? Why do we even care? So I've listed a few disciplinaries that will help you answer these three questions. If you're interested in 1 and 2, you can use numerical analysis, find a different integration algorithm that will help you integrate better. It might help, but it's still, as I found out, it's still going to give you these. So that's not it. And over the 3 years that I worked on this project, I also went into a lot of these and figuring out for myself. And when I originally proposed this talk, I was thinking of talking about more about chaos theory and the math around it, and how we can attack this problem in a computational sense. But now it's changed. I think it's better to talk about the physics, because that's who I am now. And I decided for myself that the third question is the most important. So let's talk about it. And that has to do with a really advanced method that you're going to learn in upper level mechanics called, well, probably not. You'll learn about Hamilton dynamics, but not Hamilton decoded here. So let me talk a little bit more about it. I've avoided talking about theory until now, but there's no escaping it. If you want to describe a complexity, you have to face the problem head on. So that's what I did with my cats, and my blackboard. Actually, I have a blackboard at home. So here is an introduction of sorts to Hamilton dynamics, if you ever learn it. But what it basically is you try to write down the energy. In some cases, called the Hamiltonian. It's a function of the position and the momentum of the particle, and also it might change in time. So as you see, the energy is increasing, and that changes in time. So this is really complicated. And if the particle is moving, chaotically in position and in phase space, you can expect the Hamiltonian to do the same thing, which is why I plotted the energy originally. You saw that. In the second step, you learn how to describe the dynamics by differentiating the Hamiltonian. That's the change in time of the position and change in time of the momentum. So that describes how the particle is going to move. And then the third step is you just give up because it's too complicated, right? With that energy that's doing chaotically, behaving chaotically, you can't describe the dynamics in a neat sense. So that's where Hamilton-Jacobi theory comes in. It is a tool, a mathematical procedure that can help you to identify the symmetry in your problem. So we had an original symmetry. We broke it a little bit, but Hamilton-Jacobi theory can help you identify the hidden symmetry in that. And what it is you're just basically go through a procedure to get rid of the position dependent on the Hamiltonian. And see if the Hamiltonian doesn't depend on the position, then these are conserved. It doesn't change in time. And so you have a Hamiltonian that doesn't change in time. You can also treat time as a coordinate and find the corresponding momentum as well. And then after that, you're just going to have a constant Hamiltonian, which we like, right? It's just a line instead of that wiggling sorts. And then the last step is to describe the less complicated dynamics. So with that, let me tell you how I tackle this problem. So this is the steps. It's called perturbative Hamilton-Jacobi theory. It's perturbative because we are going through a few successive steps to extract the symmetry in this broken figure. Right? The wave is really large. The particle is small. So we're going to extract the symmetry from it. And then after all of that, you're going to be left with the remainder, which is the chaotic part. And that's how we're going to describe it. So you start with first order, which is the most obvious symmetry that you have, which is cylindrical symmetry. And that is going to reduce a problem from 3-dimension to 2-dimension. And then using Hamilton-Jacobi theory, you can bring out a constant part of the Hamiltonian and then a perturbation, H1, that's still changing in time. So Z is the time analogy to, in this case. It acts similar to, it has a function of time. All right. And then from there, you can use Hamilton-Jacobi theory again to shift into the frame of the wave. So it's now standing still, and it's not moving anymore. And from there, it turns out that you can reduce it to a one-dimensional problem. And we like one-dimensional problem in physics because it's integrable, is what we say. You can always find some sort of solution to it. And from there, lo and behold, you get the resonance condition. So that's just first order effects of the wave doing its thing, right? The wave is perturbing the field. And from there, we can describe the resonant interaction through that perturbation. Right? So simple so far, but the last step is where I drove the wave. So I increase the wave. It's really large. And you have different effects of it going on. We have broken symmetry, and then you can also think of the harmonics of the resonance as an object in itself. So the particle is interacting not with one harmonic, one value of n, but with multiple values of n. So whenever we have many bodies in physics, it can lead to chaotic motion in that way. And it's really amazing in the sense that after you've gone through, so I don't show it here, but after you've gone through those steps, you're gonna get a Hamiltonian of the form of a pendulum, which is a ubiquitous problem that you learn in freshman physics or introductory physics. So that's really cool. You can reduce the complexity to something as simple as a pendulum, which you can study. And so from there, that's the description of resonance. So the next slide I have shows you a really satisfying description of when chaos emerges. So with second order effects, instead of one resonant velocity, which is the locations of these peaks, we have an island. So there's an effective width to the resonance at each velocity that the particle can interact with. So instead of just one peak, you have an island. And so from there, you can see if you have overlapping islands, then the particles can move around. So in this simulation, in this video, these are the particles. They are located at different resonant velocities, so they're interacting with different harmonics originally. But depending on the amplitude of the wave, the islands might overlap. And then when they overlap, you can see that the electrons can move from one island to another, and then it does that. So let's play the video. Yes. So in the first case, in the first panel, right, you see the islands are really well separated. So particles are moving within those islands. They're trapped. They interact resonantly, but there is a limit to the interaction. And when the islands start to touch a little bit, you can see some of the orange particles here move from here to there. These ones don't do anything. And the red particles move up a little bit. And down here you can see there are very few red particles. So that means these ones are really energized, really scattered because they move up here. In this last panel, because there's so much overlap, you can see how particles can just wander everywhere in phase space chaotically. So if we go back to, so if we move forward, I'm showing the previous figure with a little bit of a change. So I'm also plotting the pitch angle instead of just the energy, and the red and the black are chaotic and non-chaotic particles. Stochasticity is another terminology for it. And so from here, you can see from these sort of plots, right, when the particles are doing this, they are interacting with one mode, and then randomly, they can escape one island and move to another. That's where they're doing that. It's called resonance crossing. They're crossing multiple islands. And because at any point in time, they can be anywhere, it causes some sort of randomness, unpredictability to their behavior. So you can't tell when they're going to do that. But at least we know what is causing that behavior, what's driving their motion. And we have a certain constraint on the motion. So can you play it again? We can have a sort of measure by calculating a function of this resonance width in terms of amplitude, and then see and then be able to tell which particle is going to be most likely to cross a resonance. So at this point, it could be probabilistic. There's a probabilistic description to this interaction as well. I'm not going to talk about it. So yeah, this is the answer to the original question. We can describe chaos this way, and we can describe how it emerges from overdriving the wave. And you get that by doing really complicated math, which is it might be worth it, but to me it is really worth it, because the theory is really that way. So you also have a sort of a similar, kind of like a fun analogy that I find. So in these plots, these are the ones that are actually published in the paper. I'm just plotting it a little bit differently. So this is energy versus angle. So instead of just velocity, I'm plotting things in radial, in polar domain, right? This is the radius of the velocity, and that's the angle of the velocity space. And these are resonance conditions. These lines are resonance conditions. You can see, so I haven't described the color, and it's a really complicated thing that has something to do with chaos theory. But basically, whenever you see really blue, that means particles are being attracted to it. So that explains why those particles are trapped within the islands. Because when they're close to that resonance condition, they're being attracted to an island. And you can see the colors align really well with the resonance condition as well. So that is a pretty amazing agreement. And in the language of chaos theory, if you're interested in the math, these islands are called attractors in the mathematics term. And overlapping means you have a mixing of two topologies. You have two surfaces which are mixing together, and you're describing what things are doing on that surface. So yeah, that's only for the sake of description. Oh, and also you have these sort of analogy with the seas and islands, right? Because you can have well-defined islands, and then in between the islands, those are seas where the particles just don't care and they're just popping up and down randomly with small amplitude. So if you don't care about the resonance interaction, you're in these sort of positions. You're just floating at sea. And if you're interacting resonantly, you're wandering in the islands. And if the islands overlap, you can wander everywhere inland. So that's a pretty interesting analogy, I find. So to end this talk, I just want to summarize the steps that we do here. The important thing is in physics, we care about idealizations because those give us symmetries that we can study well and define it, and just we can have a well-defined description of it. So so from there, we can start with a complex thing, identify the symmetry, take it out, and then whatever is left of you is interesting physics. So that's what we did. We start with a simple system, which is where you have this sort of picture, right? Parallel waves, things are rotating in the same phase, and particles are energized, they're counterpropagating. And then we break the symmetry laws. And then from there, we can find a measure to quantify how the symmetries are broken. And that gives you a description of chaos. So yeah, that's all I have. Thanks for listening to me. It's wonderful. And yeah, if you have any more questions, let me know. Yeah, does anybody have any questions? Great. Well, if anybody does have questions, yes, go ahead.
Could you talk a little bit more about how this applies to what you're learning now about turbulence?
Right. Yeah. It's exceedingly more difficult in that case as well, because not only do you have wave pouring energy into the particles, from large to small scales, you also have particles interacting with the waves and the fields around it. So that causes field turbulence. And in that description, you can't describe it as a simple fluctuation like a coherent wave, but it's just intermittent fluctuations in that. There's no wave anymore because the particle and the wave is interacting two waves instead of just one wave here. It's sort of an idealization as well when I assume that the wave just pour energy into the particle, but in certain contexts, that is acceptable, and it's in other contexts it is not. So you have to think about it. And right now, what I'm studying in the subject that I'm studying, it's much more complicated. You also have a lot of particles interacting at once. So it's not just the electrons, it's also the ions as well. That goes into the graph, the dispersion relation that I had up here. This is already a sort of idealization, or a sort of simplistic way to look at it. In reality, these wave modes couples with each other as well. So they don't just stand alone. They can have energy transported between them. And that causes much more complex, for much more complex things.
So can the Parker solar probe kind of observe similar behaviors of running on solar winds?
Right, yeah, so that's actually one of the mission objectives of part of solar probe. Because before we only have probes that are around 1 AU, which is the radius of the Earth. No. The distance from the sun to the Earth. 1 AU is much larger than that. So before we only have probes around, and we kind of know that it is turbulent in the solar wind, but we don't know how that is going to evolve. And the theory, people have theorized that you're just going to have larger and larger fluctuation amplitude as you go into the sun. It's a reasonable thing to do, but when we send the Parker solar probe there, we find much more complicated behavior. So it doesn't just increase, it does something else as well. They have a lot more complicated dynamics. Another question.
Second level, is it the entire married or system either inside the treating material that we can, if we also in the treating material, if we the symmetry there, we can see the gas agility signal. Second, harmonic generation. So, in your talk, I have anything that was said, but I curious how was that the second signal.
How I'm breaking that symmetry in my case.
Yeah.
Well, it's because you have so again, right? The picture is you have a slanted wave, so you can in fact decompose it using a sort of Fourier transform-like technique, and decompose it into an infinite amount of Bessel functions, if you will. So instead of sine or cosine, it's Bessel functions that spans the space. And so from there, you can see this wave as an infinite amount of these sort of waves. And so when you overdrive it, the particle is not just interacting with one wave, like this picture, but is interacting with an infinite amount of waves that are really large. So that interaction breaks the symmetry in a sense. Yes. Right. Right. Yeah. So in a simplistic sense, one of the most simple system that we can talk about in terms of chaos is like the double pendulum, right? Which is a case where you have the second pendulum causing a torque on the first one, and that torque breaks the symmetry that a usual simple pendulum has, and that causes the chaotic motion of the particle. So in a sense, it is the same behavior. This pendulum is interacting not with gravity, but with the torque caused by this second pendulum. So yeah, that's in fact, I think most of the dynamics that I've dealt with can be reduced to that form. So in a way, that is a ubiquitous Hamiltonian system to work in.
Great. Well, if you have more questions, you feel free to stick around for a little bit in case people come up and ask you. If not, let's give one more round of applause. Yeah, so in case you don't know, we are CU Prime. We're a group that's devoted to diversity, equity, inclusion within the physics community on campus. So we're student-led undergrads and graduate students together, and we're for students as well. So if you'd like to get involved, we are actively recruiting people to help out with CU Prime. And we do always have things like this talk series. We have a mentorship program as well, and a class that we run each fall that some of you have been in. So also, if you'd like to provide feedback, please take a minute, scan this QR code just to let us know how this talk went. If you want more pizza or anything like that, or different types of pizza, or I don't know, we can order a cake. Who knows? Yeah, great. If not, our next talk tentatively is in 2 weeks. And we will see you then. Feel free to grab some pizza on the way out. Thanks, guys.